lecture that we missed last week. So let me go over the strengthening mechanism due to making a material into a composite material. What is a composite material? Composite material, as you probably know, is a combination of two different materials that are totally different in properties, and when you combine them, they give you properties that are somewhere in between the two. So um, this one relates to what are called eutectic composites. So eutectic, what is eutectic? Eutectic is a combination of two metals that melt at a temperature lower than the melting point of either of those two metals. So when you combine them at a certain percentage, you get a combination that is of a lower melting point than the two. And while it is forming, it also reinforces the other material. And it can form fibers or different faces that reinforce the matrix material. So in this case, for example, if you take this particular alloy, a metal alloy, and you cool it in a certain form that those grains will only form in one particular direction. When that is formed like that, then it is stronger in the direction of those grains, but its properties might be lower in the thickness direction that is perpendicular to the formation of those grains. So this is one of the processes by which turbine blades are formed. So they are taken from the melt and solidified in a certain form so that all the grains will form in one single direction only. So when you do the unidirectional solidification, then it is stronger than if you had just made a combination or just let it cool in a non-uniform manner. Okay? We already talked about laminated composites at the end of the last lecture. So if you have rubber type of a material that is laminated between sheets of a metal, then this rubber by itself will toughen the sheet of material. So if a crack is formed and it is crossing across this plate, it will get stopped by the rubber layer. And this is one of the other advantage with this kind of a composite is that it has got fantastic sound absorption capabilities. So this is the type of alloy. It's not really an alloy in the real sense because you are not really combining the two, but in the macroscopic scheme of things, you are combining two different materials that are totally different in properties from each other. So this is the composite material that is used for, say, something like the 1OK center. I mean, you see the bright shiny surface outside the 1OK center, right, in Tulsa. So have you ever wondered what it is made out of? It is made out of these kinds of laminated composites. And we have a manufacturer of these kinds of composites right here near Tulsa. Okay, and this was based on a patent that was developed at Oklahoma State University, believe it or not. Okay, so it gives you fantastic sound absorption properties as well as impact properties. And the other advantage is that because it is made like this, you can make it into some kind of a form or shape that can be used to kind of It is it's a U type of uh, hockey stick type of a thing, and you just push it between layers of another plate, a laminated plate, so that it fits in very nicely and um, completely locked in place. I'll probably have to draw it for you when I see you in class next week. Okay. So what are some of the advantages? The advantages are that um, the modulus in different directions um, are slightly different, and uh, you get very high strain as well as strength for using this kind of a material. I'll let you look up the explanation for this graph in the textbook, and you should be able to figure out, what those are. And the other advantage is that, so suppose, for example, uh, if you had a material that is made from different combinations of bonds. Say, for example, if you had simple hydrocarbons that have very low amount of covalent bonds. So the more the covalent bonds there are, the higher the strength of this material, of a material. And if you increase the amount of covalent bonds as you are drawing this material into a fiber type of a material, then those fibers will have extremely high strength and high elastic modulus, or Young's modulus. And this one shows you the properties that are, if you have a polymer material, its specific volume reduces below a certain temperature. So it is totally solidified below this temperature, which is called the glass transition temperature. So above that temperature, it can expand and increase in volume. So what is the significance of this is that it has the highest strength below the glass transition temperature, but it is not very tough. Um, these are figures I added so that you can go and look it up. And for example, if you had a material that has got liquid crystals, crystalline materials, so the higher the crystalline material, the higher the ultimate tensile strength of polymers. Okay. So what are the advantages of making fibers out of these materials? Fibers are strong in the direction of the fiber drawing, and they are not very strong in the opposite direction. So even a material such as silk or spider webs, they are extremely strong for a unit volume of the, or unit weight of that material. Okay, so you can use them to reinforce different kinds of applications. So even a material such as silk, it has got a stiffness of 10 gigapascals, and it has a strength of 1.1 gigapascals. Compare that with carbon. Carbon, the stiffness is much higher than that, but the strength is like 4 to 5 gigapascals. And nowadays, you even have carbon fibers that are of strength like 10 gigapascals. So here it shows that as 4 gigapascals, but 4 gigapascals is a lower strength material and it has got a stiffness of around 300 gigapascals, but you have much higher strength than that. And the other advantage is that the density of these materials is much lower than that of high strength materials such as high tensile strength steel. So you do not need to increase the weight of your component for getting the component to withstand the same kind of loads or tensile stresses. So which means that you can strengthen the material, but you don't have to increase the weight of your component. So that is the big advantage with composites. So this again shows you the tensile strength of thermoplastic materials. So some of the thermoplastic materials are nylon, PBT is polybutylene terephthalate. Polybutylene terephthalate is a polymer that is used in a number of automotive applications. Like, they are trying to use this kind of a material in say ducting and things like that, where you need high strength as well as ability to withstand high temperatures. The other material is polyaryl ether ketone. It is called PEEK, and the big advantage with PEEK is that it is also one of the most biocompatible materials. So people are trying to use PEEK in bioimplant type of materials. It is very lightweight, so it's not like putting in a titanium implant. And PEEK is also strong, but it has got also properties that are very similar to that of our natural bone. So it will not create issues with breaking our bones if you let it be in the body for a long time. I know that I'm jumping from topic to topic, but just going by whatever information is on the slide and trying to explain that to you. So let me go forward and go to the next topic that I want to discuss, which is creep. So what is creep? Suppose you have a component that is at a constant stress and it is also experiencing high temperature or elevated temperatures. So what happens? I do not know if you remember what you learned in your material science ENSE 3313 about creep, but what is creep? Creep is the process by which a material will deform at elevated temperatures as a result of a constant stress. And depending upon the stress, it will deform, and once the deformation goes beyond a certain limit, it will fail and it can fracture. And what is that magical temperature beyond which creep processes will start affecting your component? Again, just like the differentiation between hot working and cold working, that is the same temperature. So above half the melting point in degrees Kelvin, the material will start having a tendency to creep. Below that, it will not creep that much, or it will typically not lead to failure unless you increase the stress. So when it starts, if the creep process is active, what happens? So as soon as you apply the stress, And this is a typical creep curve where you plot the time, which is typically in logarithmic terms. And logarithmic is in base 10. So logarithmic time versus the strain. So as soon as you apply the stress, it immediately expands and stops. So it withstands a little bit of strain in a very, very short time. And this could be in terms of maybe less than an hour or something like that. Or, it could even be in terms of minutes. And then it starts creeping very, very slowly. So this is a constant rate at which it creeps. So this is called the strain rate of creep strain rate. So this one is called the first stage of creep. This is called the second stage of creep, and this is called the third stage of creep. So the creep rate in the second stage is called steady state creep rate because it is most of the time it is constant. So based on that, you can determine whether or not a component is going to fail and how long it is going to last. So if you know that a component is going to be experiencing creep, you know how long a component is going to last under those stresses and temperature conditions. So if you are replacing a turbine blade, if you are placing a turbine blade in this kind of an environment where it experiences stress as well as temperature, elevated temperatures, then you know how long that turbine blade, how long you can wait before you have to replace that turbine blade based on this. So you have equations for doing that. Okay, and beyond a certain point of experiencing this strain, then the material has started creating a lot of small holes, and they will start becoming big, and then the failure will just take off. And in the third stage, you have a very little time left before this component will fail catastrophically. Please go back and check your textbook about this process. I'm not sure that you are going to be able to understand everything that I'm talking about creep in this one particular lecture or one particular slide. So, how does creep change with increasing temperature? Let's look at that first. So if you plot the strain versus logarithmic time at different temperatures. So if you, at the lower temperature, it will take you longer for this component to fail and get to the third stage of creep. As soon as you increase the temperature, it goes into the more critical stage of creep. So it takes you less time, it gives you less time for this component to last at that temperature, at the same stress. You keep the stress the same, but you increase the temperature. And if you are very close to the melting point of your component, melting point of the alloy of your component, then you hardly have any time left before this component will fail. So it just tells you that as you increase the temperature, the time before which the component will fail decreases drastically. But suppose you keep the temperature the same and you just increase the stress that you are applying on the component. It will again it will undergo the same kind of a failure. So at a lower stress, it will take a long time for the component to fail. You get more time before it will rupture. But as you increase the stress at the same temperature, the the creep curve will shift to the left, and beyond a certain stress level, you are treading on dangerous waters. So that component will fail almost instantaneously as soon as you go beyond a certain stress level. So this is in this case, it is a power relationship for the increasing stress, and it is an exponential relationship for the increasing temperature. Now, it can be the creep time for rupture can be represented as an as a uh, relationship that is exponential also. So you can represent it as a sigma dot. Epsilon dot is the strain rate is proportional to exponential minus Q over RT. So Q is the, what is Q? Q is the activation energy for the creep processes to start. Okay, so for every material there is something called Q, and this could be different for different temperatures. So as the temperature is increasing, Q will start decreasing. So what are some of the important points? In the second stage, the creep rate is called the steady state creep rate. So this alone determines the time you have before the component will fail or rupture. As soon as you apply the stress, it will apply a certain amount of strain, and but at this point you have some strain hardening taking place and some recovery also taking place at the same time, because this is a diffusion activated process. So the strain hardening and recovery will counteract with each other, which gives you a steady state creep rate. So it's a constant creep rate in this time range. The strain hardening is the primary process, the creep process, where you are increasing the resistance dislocation. So the more the deformation that is taking place, the more the dislocations will pile up on the grain boundaries. But what is also happening at the same time is that there is a balance between the two because of the diffusion processes taking place. So that's why you have a constant strain rate in the secondary region. But beyond this secondary region, you have lot of necking and voids all forming, and those voids will all start linking up with each other and completely make the material extremely weak, and the material will have hardly any time at all before it will completely fail. So that is the whole concept of creep versus time. Okay. So we have done this. Dr. Jay Hannon used to do a lot of work on creep testing of um, some aluminum alloys. A356 is a typical aluminum alloy, and you can see this. So this is a replica of what you saw in the one of the previous slides. So at 375 degrees centigrade, this component will last for almost ever. Okay, so they stopped the test and they didn't do any test beyond that. So up to 420 degrees centigrade, nothing much happened, even though there was a lot of strain that was introduced into the material as soon as you applied the load. But beyond 420 degrees centigrade, say 500 degrees centigrade, as soon as you applied the load, the component failed, say within about an hour and a half at 500 degrees centigrade. If you increase it to 540 degrees centigrade, it failed at almost like half an hour or 1 hour. So what is this magical temperature? 540 degrees centigrade. 540 degrees centigrade is close to the melting point of aluminum. Aluminum is 661 degrees centigrade. So you can see that if you use a temperature that is very close to that of the melting point of aluminum, the component will fail almost instantaneously. So the whole thing can be represented as creep rupture, which is more important than creep strain. So you want to know how long the component will last at a particular stress and temperature. So you plot this at different temperatures and stresses. So this is stress and this is the temperature at different temperatures. So at 540 degrees centigrade, so this is for this could be for an nickel-based superalloy. S590, I don't remember exactly. So if you can please go and take a look at what is alloy S590, you can find out the composition of that alloy. So at 540 degrees centigrade, what happens? Your rupture time can be, as long as you stay below 500 megapascals, you have infinite lifetime. But as soon as you go beyond a certain stress level, then your component can fail at a much shorter time. So from this, if you check it off, say for example, if I tell you what is the rupture time for this component at say 1200 degrees F and approximately 500 megapascals. So if you plot a line from 500 to here, so what is this time? So this is approximately 2 hours or so. So you can see that if you go very close to that line, then your lifetime will decrease drastically. And so 1040 degrees centigrade might be very close to the melting point of the alloy. So that's why you have hardly any time left before the component will fail. So if you want this component to last forever, then you cannot apply more than 10 megapascals. So it really decreases the engineering usefulness of this component if you want to use that at that temperature and stress level. Otherwise, you have to change your composition of your alloy. So again, as I said to you, but if you want the component to last for a very, very long time, then your creep rate is more important than your material. So if you want to look at creep, so you plot the creep rate versus your stress level. So it will, you can, from this again you can plot what is the safe stress level and what is the safe temperature level. From that you can determine what is good for your component, usefulness of your component. Okay, and one thing to note is that FCC is close pack structure, so you have less diffusion, which means you have less creep rate and better creep resistance. So FCC type of materials have better creep resistance than BCC type of materials. So if you plot the steady state creep rate versus the temperature here is given in terms of inverse temperature in degrees Kelvin. So R is it's a constant, and those numbers will be given to you. So from that you can calculate that for the same stress level. So you have the enthalpy required for the process, for the creep process. So from that you can calculate what is the lifetime of your, or what is your creep rate for your particular component. So if you know the creep rates and if you know the temperatures, you can actually calculate the enthalpy at a constant stress. So you might find the equations and things like that in the textbook, and I will definitely give you some problems to solve based on this one. And again, as I said to you, creep is a diffusion controlled process. So which means that you can represent the diffusion coefficient equal to D0, which is a at the diffusion coefficient at a very low temperature. So if you know the temperature, you can actually calculate what is going to be the diffusion for at a particular temperature, and the delta H will be given to you for self-diffusion. So if you can calculate that, then you can calculate what is the D for the particular process. And as I said to you, this increases the diffusion increases drastically beyond a certain temperature, and that temperature is half the melting point in degrees Kelvin. So if it is above or beyond half the melting point, then your activation energy for self-diffusion will equal the activation energy for creep. So the creep processes are much more active beyond half the melting point in degrees absolute. So what are some of the important points to understand? Important point to understand is that creep is time dependent strain. Therefore, you can quote life versus stress for a fixed temperature. I know that it says here approximately 0.4 melting point, but it is 0.5. Really speaking, it is half the melting point. And again, it is a diffusion control processes. So these dislocations will start climbing. They are not just moving in one plane alone. They also go and activate themselves in the different planes. So they can climb, or they can also move because of the temperature conditions. And again, as I said to you, diffusion is less in close pack structures. So FCC has got much better creep resistance than BCC. So this is again, you can see the deformation mechanism maps, and you will find that in authors like Ashby. So um, he has these deformation mechanism maps that will show you what component at what temperature and what stress level is safe to use based on that. So where is all this important? Say for example, if you have a power plant, you have a design life of 30 to 40 years. So what we do is we test these materials and we get short-term data, and based on that we are going to extrapolate that to say to see if your component is going to last for that long or not. So the most common extrapolation is Larsen-Miller parameter. So if you know that, so it will give you temperature times C, which is the Larsen-Miller parameter, plus log T will be given to you. So based on that, you can actually calculate the rupture time for your component. I'll give you some examples of that for you to view and understand and solve problems. Okay. So again, what is actually happening at a microstructural level in creep? So when you are applying, when creep processes are active, as I said to you, it is a diffusion control process. So atoms are going to be just going all over the place. So when that happens, there is extra stress being put at the corner of the grains. And at the corner of the grains, then you suddenly start forming a void. And not only that, at elevated temperatures, these grain boundaries suddenly become extremely weak. And they become like, suppose you take ice, okay? And if you start melting ice, those edges of the ice cubes become extremely soft and smooth. So that's the same thing that happens here in this kind of a material. So it just creates these kinds of cracks, and then the grains will start separating out from each other, and then they will start sliding against each other. So at elevated temperatures, especially beyond half the melting point in degrees Kelvin, the grains will have a tendency to slide over each other. So when it slides over each other, those voids will start becoming big and start linking up. So that is what is happening. That's what will happen in the third stage of creep. So once that happens, you cannot stop it, and the component will fail in a catastrophic manner. So you can see that this is the microstructure of this A356 that Dr. Hannon tested here. So you have these voids of porosity, and they will start linking up with each other and start failing very drastically. So in the secondary stage of creep, these are not that critical, but beyond this, in the tertiary stage, all those microvoids will start linking up, the grains will start sliding over each other, and then they will start linking up and creating these big micro cracks, or macro cracks, and will cause the component to fail very drastically. So how do you protect your component against creep? the most obvious thing is to use the component below half the melting point if possible. But you may not have a choice for that. Okay, so you use crystal structures that are less prone for creep. So that would be face-centered cubic. And even after face-centered cubic, use solid solution strengthen the material. Or you use single crystals. So the less grain boundaries you have, the less tendency for the material to fail. So they have less tendency to slide over each other and fail. So when you do directional solidification of your component, then they have less tendencies to form grains or a lot of grains. Or you try to create very fine precipitates to pin the grains and the grain boundaries so that the grain boundaries will not move at all. So that's what people have tried to do in the case of nickel-based superalloys for turbine blades. So they have precipitates of Ni3Al, which does not melt with temperature, and they start precipitating very uniformly, and then they will start locking up the grain boundaries and preventing them from moving during the creep process. So creep mechanisms are slightly different at different temperatures. So at a very low stress and high temperatures, you have what is called vacancy diffusion through the grain interior, and that is called the Nabarro-Herring creep. And in that case, the steady state creep rate is given by this kind of a relationship. You can also have what is called the Coble creep. Again, these are all different ways of representing the creep process. So don't get too caught up in the names, but it's just that these are the two creep mechanisms that are active at different temperature ranges. So at high stress and high temperatures, you have the Coble creep taking place, and you can, so the smaller the grain boundaries, the higher the sensitivity for the creep rate. Okay, so that's one of the reasons why you try to increase the grain size, which will in turn reduce the steady state creep rate and increase the rupture time for your component. So if you increase in grain size, you can suppress the Nabarro-Herring and Coble creep. So creep mechanisms depend on the stress, temperature, and grain size. So reduce the stress, reduce the temperature, increase the grain size. Those are the three things to note in order to make a material or a component withstand creep effectively. What is it again? Reduce the stress, reduce the temperature, and increase the grain size. So please note that. So again, as I said to you, the grains could be very similar to that of an ice cube. So if you increase in temperature, those grain boundaries will become weak, and then they will start sliding against each other. They will also start elongating and slide against each other. So if that is the case, you do not want, so that's one of the reasons why you want to reduce the temperature. You want to reduce the stress so that the grains will have a lesser tendency to elongate. So this is called the deformation mechanism map. So it tells you what mechanism is active in what region. So This is the normalized tensile stress. So it is a tensile strength divided by the, no, it is the stress that you are applying divided by the tensile strength. So depending upon how much stress you are going to apply, these stress, I mean these creep mechanisms will get active. And it also tells you, and you can also figure out what is the safe temperature and what is the stress level that you can apply for your component from this mechanism map. So as I said to you, C is the Larsen-Miller parameter. So here is an example of that. So the parameter will change with temperature. So that parameter is equal to the temperature 650 is, so you can actually see the Larsen-Miller parameter, and I don't know where he got the 10, ln 10 to the power 5. I'm not really sure where he got that from. So that could be a constant. ln 10 to the power, 10 to the power 5 might be, no, 46 might be a constant. And he is using natural log here instead of log t. Okay, so from that you can actually calculate the stresses for each of those temperatures. So you can see that if you increase the temperature, then your safe stresses actually decrease. Oh, okay. Oh, 10 to the 10,000 hours. 10,000 hours is the, so that is 10 to the power 5. Okay. 10,000 hours, 100,000 hours. So you want the component to last for 100,000 hours. And so if you increase the temperature, then you can only use this component at 85 megapascals or lesser. You got it? So you can actually calculate that, and this is just plugging and calculating those numbers from this. So C is a constant. I don't know where he got that value of C from. Okay. But if I give you this kind of an equation, I'll give you the constant. So you should be able to calculate that to determine the values of the safe stresses. Okay. Again, you have processes of superplasticity, which is active in certain types of alloys only. Say, for example, aluminum or titanium and things like that. So what are you taking advantage of in this kind of a process? Where do you need superplasticity? So if you have some components that you cannot easily form So you reduce the grain size in such a way that they can easily become super plastic. So you can easily make a component into a certain form based on this process. So what kind of materials can be used for elevated temperature applications? What do you need for elevated temperature applications? First of all, you need high melting point, because where does creep become active? Beyond half the melting point in degrees Kelvin. So which means that if you use a material that has got a very high melting point, that means it becomes safer to use. High modulus of elasticity, low diffusivity. So less creep active processes are active at this temperature. You need good thermal fatigue resistance, and you also need good oxidation corrosion resistance. So what are some of those types of materials? Nickel and cobalt based superalloys. And you use tungsten and molybdenum as solid solution strengthening, and it also lowers the diffusivity of the materials. Then you have try to use these materials with coarse grains. You don't have a lot of grains, which will increase the tendency for the material to creep and slide against each other. You want to reduce those chances, so which means that you try to increase the number of grains or decrease the number of grains. So which means coarse grains is what you want. Okay, so these are listed as some of the materials for elevated temperature applications. So you have these blades, and you can see that if you have ever watched it in the turbine engine that is placed in the student center in Stillwater, you can see that. Okay, so if you have polycrystalline materials, your lifetime of your component becomes drastically less. If you have single crystal alloys, you can get 9 times the lifetime for creep strength, 9 times the lifetime for thermal fatigue resistance, and corrosion resistance is also much higher than that of polycrystal type of material. So reduce the number of grains, make it a coarse component, coarse grained component. It will increase the lifetime of your component. Okay, so these are again, as I said to you, increasing the temperature decreases the lifetime of your component. So again, these are pictures of that, whatever we had been talking about earlier. Okay, so let me stop here, and I will pick up for the next lecture in the next class. Hopefully we'll be able to meet in person for the next class.